yeah, so we're just going to finish up graphing transformations of sine and cosine. So let's just start with that. Alrighty. So previously, if you remember from last class, I gave you guys a graph of a trig function, and I told you guys to tell me the formula for the graph that was shown. Let's do it the other way. How about I give you a formula, and you just need to sketch out a graph, okay? So that's what we're gonna do. I'm gonna give you some formula for a trigonometric function, and then you just kind of sketch a graph for me, all right? So let's just dive right into an example. We're just going to do like 2 examples of this. So the thing will be to graph one period of the function y equals 2 sine of pi x plus 1. Okay. All right. So this is kind of like the process. I think firstly, it's always nice to label out your midline, amplitude, and the period. And then from there, it'll be pretty easy to sketch a graph. All right, so from here, we can get the midline almost immediately. So the midline is, you just need to look at the vertical shift. All right, so there's a vertical shift of +1. So that will be precisely where the midline is. It will be at the horizontal line y equals 1. That's the first thing. Very good. The amplitude. So the amplitude, you just need to see what the vertical stretch is or what the coefficient of the function is. So the function is being multiplied by 2. So you take the absolute value of it technically. You need to take the absolute value of the coefficient. It's 2, since 2 is already positive. So that taking the absolute value doesn't change anything. So the amplitude is 2. And the period, you can recall, you have to do 2 pi divided by the horizontal compression or stretch. So the horizontal compression here is pi. Okay, that's what the input is being multiplied by. So the period is 2 pi over that horizontal stretch. And, you cancel out the pi's and it will just be 2. So that's the period. So we just gather this information and that makes graphing pretty easy once you have all these data points here. All right, so this is kind of what you do. You just can draw like an XY axis. Okay, so I like to personally, I go to the midline and I do a dotted line. Okay, very good. Now, so just recall, we're doing sine. So just off to the side here, you remember sine has kind of this shape. That's what one period of it looks like. Okay, so we just need to go and do that. So we start at the midline. Go right here. And okay, so all right, sorry, I'm just like a little all over the place right now. So the period's 2, so that means it's going to finish 1 cycle in 2 units. All right, just hold on 1 second, sorry. Okay, sorry about that. So I like to just go to where the period's going to be and mark that off on the x-axis. So it's 2 in this case. So we know that it's going to start at 0 and end at 2. And then what I like to do is I like to divide the interval from 0 to 2 into 4 pieces, okay? So the way you do that is you divide it in half first at 1, and then you divide each of these halves into a further half. So this will be 1/2, and then in between 1 and 1/2, in between 1 and 2 will be 3/2. Okay? Good. All right. So now we need to follow this kind of basic shape. It's going to go like that. All right. So just make this a little bigger maybe. So it's going to look like this. Um, good. So next we're going to have like the maximum point. So that we need to go up 2 from the midline. And that's going to happen at the quarter mark. Okay. So we go up to 2 here. And then next it goes down back to the midline. At the next quarter mark, it will go down there. And then it's going to end at the midline like that. Okay, and then you can kind of just draw a nice smooth curve through all this. Okay, so that's pretty much the deal. I apologize if that seemed a little all over the place. We're going to do another example, and hopefully it's a little more clear. Okay, so essentially, I think the most important thing I did was I put the period down on the x-axis. In this case, it was 2. And then I chopped from 0 to 2 up into 4 pieces. See, I chopped it up from 0 to half, half to 1, 1 to 3 halves, 3 halves to 2. And then it goes in this shape on that domain. All right, so that's pretty much the deal. And we'll do one more example of this. All right, so any questions so far? All right, so let's do one more example. Okay, so graph 1 period of y equals cosine of 2x minus 1. Okay. All right, so again, let me just list out all of the data points. So the midline is, you just have to look at the vertical translation or the vertical shift, and that's y equals minus 1. The amplitude, so you take the coefficient, so you take the vertical stretch. In this case, it's just 1, since there's no vertical stretch. So amplitude is 1. And the period, so remember, to find the period, you do 2 pi divided by the horizontal stretch. So you do 2 pi divided by 2, which is just pi. Okay, good. So that's all of our data points, and now let's go to the graph. Okay, so as I did before, I'm going to start off, let me just go to the midline, and I'll put a dotted line there. So the midline's at minus 1. Next, I'm going to plot pi on the x-axis. Okay, that's the period. That's how long it's going to take for my graph to complete one cycle. Next, what is nice to do is to chop up the domain from 0 to pi into 4 pieces. So chop it in half first. That will be pi over 2. Good. Now chop up in half 0 to pi over 2. That'll be pi over 4. And now cut the interval from pi over 2 to pi in half. That will be 3 pi over 4. Okay, now let me just go off the side and just show you guys what the basic shape of the cosine graph looks like. It's kind of like something like this. So we just need to make that shape now on this axis, okay? So we're gonna start, right, so we start at the maximum point. So if the midline's at -1 and the amplitude is 1, that means we're starting at the origin. Good, so we just have to follow this shape here. So now we just use our tick marks that we cut our domain up into 4. So we go here, then we go down at pi over 4. We go down to -2 at pi over 2. We go back to the midline of 3 pi over 4, and then we go to 0 at pi. All right, and then just connect this with a nice smooth cosine wave. And that will be it. That will pretty much be all you have to do. Okay, so I hope that was okay. So just please let me know if like anything was unclear.
I have a question.
Mm-hmm.
For the first one, actually, um, why does the point over 3/2 go only to the midline if the amplitude is 2?
So the point at 3/2 is at 0. This is the x-axis here.
Mm-hmm.
So are you asking why it's 0 at 3/2?
Yeah, why wouldn't it be -1 if the amplitude if the midline is 1
Mm-hmm.
and you go up 2 and then down 2? Why
Yes.
would it not go past the?
Yes, you are absolutely correct. And I copied it wrong from my notes. So thank you. Yes, I apologize for that. Yes, so what Camille said is that the distance from the midline to the minimum point ought to be 2 because the amplitude is 2. And she saw that that distance is not 2, it's 1. So there's something wrong with this graph. And yes, there is definitely something wrong with this graph. So pretty much the point at 3/2 has to go down 2 spots from the midline of 1. So you go down 1, 2 at -1. And that's where the point at 3/2 is. Yes, very good. Good observation. So yes, now with the right thing, we can make a graph. Very good. Awesome. So any other questions? Okay, so not that bad. So just on homework 10, you'll just be asked to graph 2 of these, extremely similar to these examples I just gave you. Okay, so you can use the notes as a guide. All right, good. So now let's move on to the heart of tonight's class, and that's going to be the inverse trig functions. So let me go to let me just go to a new page. So developing an inverse to the sine and cosine functions. Okay, good. So first, before we start this, how about we just recall the graphs of sine and cosine. So let's recall the graphs of sine of x and cosine of x. Okay, so let's just recall what those look like very quickly. Okay, so this is the same picture from last class. So, so the top one is sine of x and the bottom one is cosine of x. Okay, so the problem with finding an inverse to these functions is they're not one-to-one. Okay, if you remember from some homeworks ago, like a few homeworks ago, a necessary condition for a function to have an inverse is that the function has to be one-to-one. Okay, because when you take the inverse function table, you're going to get an output going to multiple, one input going to multiple outputs, which is, of course, not allowed for a function. But if it is one-to-one, you do get an inverse. Okay, so we have an issue here. These two functions, they fail the horizontal line test. You can see that pretty easily. So there's no inverse yet. There's no inverse. Okay, so let me just write this just to have it here. So we see immediately that both functions are not one-to-one. So currently we see immediately that both functions are not one-to-one. So currently we have no inverse function. Okay, so that should be, hopefully that's clear. However, we can quote unquote restrict the domain to obtain We can restrict the domain to obtain the next best thing. So I'm going to now explain what it means to restrict the domain. All right, so let's put a rigorous footing on what that means. Okay, so definition, here we go. Definition. Okay, so let f of x be a function the restriction of f, that's what I'm defining, the restriction of f is obtained by choosing a smaller domain. Okay, so you have some function f. Let's say it has a domain, but you don't want to work with this big domain that f came with. Okay, maybe it's like too big. Like maybe the function's not one-to-one on that domain. Okay, but we can choose a smaller domain or a subset of f's domain and just look at that function on that smaller domain. Okay, and that's what the restriction of a function is. You just view it when its domain is a subset of its original domain. Okay, so you just restrict the x values that you're plugging in. So this will be clear with an example. All right, so let's actually restrict the function and see what this means. So example, so let f of x equal x squared. All right, so the good old parabola, okay, or the it's a quadratic function. Okay, so we can. So first of all, let me just say that the domain of this function x squared is all real numbers. I hope you guys agree. I can plug in any real number into x squared without any problem. So the domain is minus infinity to infinity. Okay, but we can restrict the function f by choosing a smaller domain. So how about we choose a smaller domain instead of minus infinity to infinity? How about we just restrict the domain to be 0 to infinity? Okay, so we just took a smaller domain for our function x squared. So what does that look like on a graph? Let's now go to that. Okay, I thought I had a picture of this. I guess not. No, I don't have a picture. So what that's going to look like on the graph, you just plug in values from 0 to infinity into your function x squared. So you're just going to get that right half of the parabola. Okay? So this left side, when you plug in the negative numbers, is not there anymore. Okay? So we're restricting the domain of the function x squared. We're taking a subset of its original domain and just looking at the function now with that smaller domain. Okay? So why do we want to do this? So look at what happened when we restricted the domain. Note here so note here that this domain restriction produces a one-to-one function. So that's why we sometimes wish to restrict the domain of a function. It's so that the function will become one-to-one on that smaller domain. And you can see now that the function x squared passes the horizontal line test on the smaller domain and hence is one-to-one.
is that the only domain you can restrict it to? 0 to infinity?
No, 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 no. You can restrict it to anything you want. I could have restricted this from like 3 to 5 or from 2 to infinity. Yeah, you can restrict it to anything that's a subset of the function's original domain. You just can't go outside. You can't make it bigger. But yeah, anything will work.
But generally, it's just kind of better to keep it like this. That way you include any real numbers that, I mean, if you want to extend the graph, I mean.
No, choosing 0 to infinity as my smaller domain was somewhat arbitrary. It did not need to be this.
Okay.
It just kind of looks nice on the graph, but yeah. So good question. And why sometimes this is attractive to do is because you can produce a one-to-one function by restricting the domain. And look, we have done that. We made x squared one-to-one, but the consequence is that we can only plug in positive numbers now. Okay, so there is a cost. Okay, so why am I doing this? We now do this domain restriction process for sine and cosine. So we now do this for sine of x and cosine of x. Okay, so we're going to restrict the domain of both functions and make them one-to-one, and hence have an inverse on the restricted domain. That's the idea. Okay, let's start off with sine. All right, so let's go to the graph. Let's see. Okay, so let's make this bigger. Okay, so as I said before, this guy fails the horizontal line test, okay? But we can restrict the domain of sine of x so that it becomes 1, 1 on this domain. So where are we going to restrict the domain to? What are we going to restrict the domain to? Well, the conventional choice is to restrict it to minus pi over 2 to positive pi over 2. And again, this is an arbitrary choice mostly, okay? We're just doing this so it becomes 1-to-1 on this domain. Okay, so we're just going to consider the piece of the graph right here from minus pi over 2 to pi over 2. So let me just write that. So we can restrict the domain of sine of x to, so I restricted it to minus pi over 2 to positive pi over 2. So I shrinked the domain by a lot. Originally, the domain of sine of x is all real numbers. I just made it this closed interval, minus pi over 2 to pi over 2. Okay, and why did I do this? So again, on this restricted domain, sine of x is 1-to-1. Okay, so let's just look at a picture of the graph of the restricted sine function. Okay, here it is. Very good. So you can see now the only part of the sine function that we are considering is this blue arc here. It's just the piece of the graph that shows when you plug in x values from minus pi over 2 to pi over 2. And this dotted line part we're not considering anymore. Okay? And you can see now very clearly that this passes the horizontal line test. Okay, and thus on this restricted domain, sine is 1-to-1. All right, so you can see that visually very clearly. Okay, and why do we want 1 to 1? It's because there's an inverse now. So since sine is 1, 1, since sine is 1 to 1 on this domain, we actually have an inverse. I should have an inverse on this domain. Okay, so hope that's okay. So here now we lead to the definition of the inverse sine function. So here we go. This is actually the formal definition. So the inverse of sine of x denoted, so how do we notate this thing? Denoted by arc sine of x. So that's the name that we give it. Arc sine of x is the inverse of the sine function. So it's the inverse of, it's the inverse of the function sine of x restricted to that closed interval minus pi over 2 to positive pi over 2. So that is the definition. You restrict sine to minus pi over 2 to pi over 2. It becomes 1 to 1 on that restricted domain, and hence on that restricted domain, you do have an inverse function. Okay, so this is not like a true inverse. It's not a global inverse for sine. It doesn't work on sine's original domain, but on this little piece, minus pi over 2 to pi over 2, you do have a legitimate inverse. So it's like a local inverse. That's what you would say. Yeah, that's like one way to word it. Okay, so how do we kind of get at the graph of this? All right, so let's now talk about the graph of this guy. So to graph arc sine, we can start with a function table for sine of x with the restricted domain of, again, minus pi over 2 to positive pi over 2. So we just look at a function table for sine of x where we're just looking at x values in this restricted domain. Okay, so we do that, and then we know how to get the inverse function table. You just have to swap the outputs with the inputs. All right, so let's first do the table for sine of x on this restricted domain. So this will be x, this will be sine of x. Okay, so I'm just considering values now from minus pi over 2 to positive pi over 2, and I would like to choose the special trig values in that interval. Okay, because we actually have nice closed forms for those special values. So I will start at minus pi over 2, and then I'm just gonna work my way up. 4 minus pi over 6, 0, pi over 6, pi over 4, pi over 3, and pi over 2. So why did I choose these inputs? Well, these are all of the inputs in the interval minus pi over 2 to pi over 2 that we have nice closed forms for sine. Okay, we know the sine evaluated at any of these inputs. So you can use the trig table and also our work on reference angles. So I'm just going to fill in now the outputs. Okay, so minus 1, minus rad 3 over 2, minus rad 2 over 2, negative 1 over 2, 0, 1/2, rad 2 over 2, rad 3 over 2, and 1. All right, so how did I get these outputs? Again, the right side is from the trig table that we talked about a few classes ago, and the left side you can use reference angles and go through that process that we outlined. All right. All right, so we're not done yet. This is just the function table for sine of x. But it's very easy now to get the function table for arc sine of x. The inverse, you just have to flip the inputs with the outputs. So now, the function table for arc sine of x, that's the inverse, will just be the inverse function table of the previous table. Okay, so from maybe exam 3, remember, if I give you a function table, you can get the inverse function table very easily just by swapping the first and second rows. So it's the same thing, where we have the function table for sine, and now we swap it to get the function table for the inverse, arc sine. All right, so I'm just going to quickly write it out, and then we'll look at the graph. All right, but really I'm not doing anything that requires much thought. I'm literally just swapping the first and second rows. So this bottom row will now become the top row. It will become the inputs. So -1, negative rad 3/2. Yeah, so I'm just gonna just fill this out. Okay, so those are the inputs, which I've gotten from the outputs of the previous function table. And now the outputs will be the inputs of the previous function table. So let me just copy that down. Zero. Mm-hmm. 5/6, 5/4, 5/3, 5/2. And there you have it. That's the function table for arc sine, the inverse of sine. And how do we get the graph? Well, you just have to plot these points now in the xy plane. So that's very simple now. So now plot these points to obtain the graph for arc sine of x. Okay, so I'm not going to do this, but I do have a picture. I mean, I can trust that you guys can plot these XY coordinates on the plane and draw a smooth line through it. Okay, that's all this is now. But I do have a picture of what this looks like. So where is that? Right, here it is. Cool. And here it is. So this is the graph for arc sine. And you can get that, again, just by plotting these points on in the xy plane. So for instance, -1 comma -π/2, that will be 1 point on this graph. And yeah, here it is. It's this leftmost point. And the rightmost point will be 1 comma π/2. And that is indeed on our function table. So this is arc sine of x. It's just this it's this arc, okay? This does not extend to infinity, okay? It's just this little piece. All right, so any questions about this process? There are a lot of kind of moving parts here. We needed to restrict the function, and then, and we had to do some more things. So just any questions before I move on to cosine? Alrighty, so now I'm going to do the same thing for cosine, but I'm not going to be as explicit with the details. I'm just going to run through it very quickly, but it's the same thing though. So inverse for cosine. Okay, so let me, yeah. So what we do here is pretty much the same thing. Copy this. Okay, so remember what the problem was. Cosine is not one-to-one, right? We need to restrict the domain so that it becomes one-to-one, and hence there will be a valid inverse. So remember, with sine of x, we restricted our domain to minus pi over 2 to pi over 2. We're not going to do the same thing for cosine. Instead, we're going to restrict it from 0 to pi. That's the domain restriction. You can see that on that domain restriction, it becomes one-to-one. Okay, so we restrict cosine to 0 to pi. And you can see that it passes the horizontal line test and is one-to-one on that restricted domain. All right, so here is the definition. So the inverse of cosine of x, and what's the notation? Denoted by arc cos, arc cosine. Arc cosine of x, so that's the notation, is the inverse of cosine of x restricted to 0, comma pi. Okay, so that was the domain restriction that we chose for cosine to make it one-to-one. Again, this is not the domain restriction you needed to do. There are infinitely many domain restrictions you could have done to make it one-to-one on that interval, but conventionally and just historically, you use this domain restriction. You restrict it from 0 to pi. That's just what has been done for forever, and it's fine. It works. All right, and what does the graph of this look like? So I'm not going to go through the function table business, but I'll show you guys the graph. And here it is. So again, it's like it's just an arc that does not extend to infinity in either direction. You wouldn't expect it to, because the graph of the restriction doesn't extend to infinity. So the inverse won't either. All right, so very similar to the procedure we did for sine, except the domain restriction was slightly different. We restricted from 0 to pi. All right, so that's the procedure, and this is actually done quite often in upper level mathematics. You do stuff like this so you can create a one-to-one function. So any questions? All right, so let's just do a few applications with these inverse functions, and then we will call it a night. So example, find arc sine of 1/2. Okay, and to deal with a computation like this, you need to ask yourself, sine of what angle is 1/2? That's the question you need to ask to answer this. So let me write this. So we ask ourselves, for which x does sine of x equal 1/2? That's how you answer these types of questions. You need to be like, okay, sine of what is 1/2? It's kind of analogous to when we evaluated logarithms. Okay, so what sine of what is 1/2? That's what we need to ask ourselves, and this is not bad. So from earlier work, both x equals pi over 6 and x equals 5 pi over 6 work. Okay, but both of these are not the answer. Okay, so but x equals pi over 6 is actually not in the range for arcsine. Arcsine does not attain this value of 5 pi over 6, so we have to reject it. So x equals 5 pi over 6 is not in the range. It's not in the range of the arcsine function. So we reject it. So we reject it. So thus, x equals pi over 6 is the answer. Okay, so that's the deal. So the takeaway of this, is that your answer has to be in that interval minus pi over 2 to pi over 2. All right? Because that's the range of the arcsine function. So takeaway, the output of arcsine of x must be in the interval closed pi over 2, the closed interval minus pi over 2 to positive pi over 2. Okay, because that's the range of the arcsine function. These are the only, it only hits values in this interval, and x equals 5 pi over 6 does not live inside of this interval. So we reject it. But x equals pi over 6 does live in this interval, so that's an acceptable answer. All right, so that's pretty much the deal here. All right, so let's do one more to kind of hit this home, but now let's do it with, okay, so I have another arcsine example, and then my third one is arc cosine. Okay, so another one, find arcsine of negative square root of 3 over 2. Okay, so again, this is the same thing as asking, sine of what angle is negative 3 over 2? Okay, so we need to find theta such that sine of theta equals negative square root of 3 over 2. Okay, that's what it means to evaluate arcsine of negative root 3 over 2. Okay, so which theta values work? Okay, so theta equals, so this is something you can, sorry. This should be arcsine of negative square root of 2 over 2. I apologize, I copied it down wrong. Negative root 2 over 2. Excuse me. Negative root 2 over 2. Okay, so we need to find thetas such that sine of theta is negative root 2 over 2.
But isn't that the input though? I mean, like, you plug that value in to get it? I mean...
Yeah, so it's the input of the arcsine function.
Okay.
But to get at this value, since it's the inverse, you need to ask yourself, sine of what will give me negative square root of 2 over 2?
Okay.
Yeah.
The input will give you that angle.
What was that?
That this input negative radical 2 over 2 will give you the angle.
Yes, exactly. It's the angle that produces negative root 2 over 2. Yes. So which thetas work? What gives me negative root 2 over 2? Well, this is by our earlier work now. So theta equals minus pi over 4 and theta equals positive pi over 4 work, but we need to reject the one that is not in our interval. Okay, excuse me, no, theta, sorry, I know I'm kind of tripping up here. No, so theta equals pi over 4 does not work because sine of pi over 4 is positive square root of 2 over 2. So this does not work, never mind. No. So you don't even need to check for your domain restrictions. So theta equals negative pi over 4 works because it's in the interval. Minus pi over 2 to pi over 2. Okay, so remember, so go up to the takeaway here. The output must live inside of this interval, minus pi over 2 to positive pi over 2, and negative pi over 4 is in that interval, so it checks out. You don't need to reject it. Okay, so this is the only answer.
Could you repeat that again? I'm sorry.
So when you evaluate these things, you need to make sure that your answer is inside of the interval negative pi over 2 to pi over 2. And
Okay.
negative pi over 4 is indeed in this interval. So it checks out. Reason being is because this is the range of the arcsine function. Okay, good, good, good. Okay, next, let's do one more with arc cosine. So find arc cos of negative square root of 3 over 2. Okay, so again, we look at cosine of theta equals negative square root of 3 over 2. So which thetas will solve this equation? Well, so you have to use our earlier work of using reference angles and whatnot. Theta equals 5 pi over 6. And theta equals 7 pi over 6. Both work, but we need to reject one of them. But theta equals 7 pi over 6 is not in the range of arc cosine. So we reject it. So the answer to this is 5 pi over 6. Okay, and again, the takeaway here is that the output for arc cosine must be in the interval 0 to pi. Okay, so that was the range of our arc cosine function. It was 0 to pi, and 7 pi over 6 is not in that interval. So we reject it, but 5 pi over 6 is, so we can keep it. All right, so that's that. Good. All right, so let's have a few more questions. So the next part will be using arcsine and arc cosine to find angles. to find angles of, yeah, so just that, that's fine. Okay, so here's what the question will look like. Example, find theta, and I'm going to draw a right triangle. And I'll give you some sides. I'll say the hypotenuse is 12 and the adjacent is 9. And I'm going to tell you, okay, find the angle theta. Find the angle theta. So how do we do this? Well, look at what we're given. We're given adjacent and we're given hypotenuse with respect to theta. So adjacent hypotenuse, that gives us the data for the cosine function, right? Cosine of theta would be 9/12, adjacent over hypotenuse. Okay, so we know that cosine of theta is adjacent over hypotenuse, but in this case, it's 9/12. So I hope that is clear. That's just the definition of cosine of theta. Okay, good, but then this implies that theta is equal to arc cosine of 9/12. Okay, because remember, arc cosine of 9/12 are the theta values such that cosine of theta is 9/12. Okay, so you get this, and now at this point, 9/12 is not any nice value, so now you can punch this into a calculator, and you will get that this is approximately 0.7227 radians, or approximately 41.41 degrees. Okay, and you can definitely use a calculator for this because 9/12 is not any of our nice values. It's not one of our nice, yeah. So that's really all you have to do for this. Let's do another one in the spirit of this question. Find theta. Okay, yeah, so before I move on, any questions? I know I'm kind of moving a little fast right now. Okay. All right, so find theta, so another right triangle. So let's do that. Here's theta. Okay, and I'm giving you hypotenuse is 10, and now I'll give you the opposite side is 6. Okay, good. So now look at the data that we're given. With respect to theta, we're given opposite and we're given hypotenuse. So that should like ring some bells in your head that we ought to use the sine function since sine is opposite over hypotenuse, and that's what we're given here. All right, so you do have to think a little bit. You have to see what pieces you're given and then apply the correct trig function. So I hope you guys agree. We have what here? We have sine of theta. Well, by definition, it's opposite over hypotenuse. And in this case, it is 6/10. Right, so now remember, this implies that theta is arc sine of 6/10. Okay, and then 6/10, or what is this, 3/5, if you reduce it, that's not one of our nice values. So you would just go to a calculator at this point and you would be like, okay, this is approximately 0.6435 radians, or approximately 36.87 degrees. And that would be the measurement of this angle theta. All right, so that's kind of nice. So that's all I would ask you for this type of question. You can definitely use a calculator. Okay, good. One more. So this is the last example, and it's a little different than the previous two. It's a little more, maybe a little more involved. Okay, so here's the last example of the evening. Compute, okay, cosine of arc sine of 1/2. So compute cosine of, and the input of cosine is arcsine of 1/2. Okay, so this is what you do. You go to the input of cosine and you call that theta. So you go to arcsine of 1/2 and you just set up a variable, theta, and set it equal to that. So you let theta, in this case, be arcsine of 1/2. Okay, so you go and do that, and then this implies. Now you go into the sine representation of this. That sine of theta will be 1/2, 1/2. Okay, so that's a conversion from arcsine to sine. These are equivalent. If theta is arcsine of 1/2, then sine of theta is 1/2. They're equivalent statements. Good, and now you draw a right triangle based off that data right there. So you draw a right triangle based on that. So you based on sine of theta is 1/2. That's the next step. All right, so let me do that. Good. So sine of theta is 1/2. That means that with respect to theta, the opposite side is 1, and the hypotenuse is 2. Right? Good. Now, the side that you don't have, call it B, and use Pythagorean theorem to find B. Okay, good. So by Pythagorean theorem, we know that 1 squared plus B squared will be 2 squared. So this would be B squared is equal to 3, and thus B is equal to the square root of 3. All right, so that's just good old Pythagoras. And now we're in a very good position. So now we go back to our original guy, cosine of arcsine of 1/2. Go back to this. Now remember, what did we call arcsine of 1/2? That's theta. Remember, that's what we set theta equal to all the way in the beginning. So this is the same as cosine of theta. Very nice, and we can get cosine of theta immediately from reading off this right triangle that we constructed. So cosine of theta, by definition, first of all, is adjacent over hypotenuse. And adjacent to theta is B. Adjacent to theta is B, and we just figured out that B is the square root of 3. So that goes up in the numerator. And the hypotenuse, well, we had that already, that's 2. So that's the answer. That's it. That's how we got it. So thus, so really the final thing here is that cosine of arcsine of 1/2, we got a nice value for that. That's the square root of 3 over 2.